Hi, we're going to do a quick introduction to graphs in this video. So to motivate for graphs, we want to maybe think about a data structure that we have studied in the past, and that is trees. We've studied general tree, but binary search tree in a lot more details. And when you think about it, trees are useful, but then there are lots of real world kind of information that cannot be represented by trees. So for example, maps. Right? This is a screenshot of Google Map, but Bing Maps, any sort of map, it's the same thing. It's and maps. You look at it, it has all these little places, right? A city, a house, a park. So those are kind of like nodes in a tree, right? And then these places they are connected by highways, roads, and etc. So so those are kind of like connections in a tree between the nodes in a tree. However, there are just a lot of things that because of the number of limitations of tree that cannot uh, in a map that cannot be represented using a tree, such as tree actually has a root, right? You look at a map, where is the root? There's not a single root. And then in a map, let's say loops can be formed, right? You can start at one place. Let's say start in San Francisco, you go around, and you can end up back in San Francisco. You cannot have that in a tree. And then also roads can have distance, right? They have lengths, and roads sometimes like even have tolls. You have to pay to get on those roads. There are all sorts of things that a tree simply cannot represent. So we need a more general data structure, and obviously that is the graph, which is what we're going to be talking about for this week and next. So what is a graph? Well, according to Wikipedia, graph is just a structure that is a set of objects, and and then some pairs of objects are in some ways related to each other. And it's just that it's very general, kind of even almost vague. So let's dig a little deeper into it. I mean, I highlighted the words objects and related. So how they are actually manifested in a graph is that the objects, they are represented by what are called vertices or singular vertex, and then the relationship between pairs of objects, they are generally called edges. So, very simply, this is a very simple graph. These are vertices. The numbers are vertices, and then the connections between these numbers, they are edges. Now, let's look at a more concrete example of graphs. So this is an example of using a graph to represent a map, as we discussed earlier. So a vertex, kind of in general, it can represent any sort of object, right? So it can contain any sort of information. In this particular case, it represents a vertex represents a city, and to represent the city, in this example, each vertex contains only a single attribute, and that is just the name of the city. And then edge, remember the edge kind of represents kind of a relationship between two vertices. And so an edge in general can again contain a number of attributes. In this particular case, an edge kind of represents the distance between the cities, and therefore it contains a single attribute that is a number. Okay, and now with this graph, so what is this graph good for? Well, it's actually it can answer a very useful question, such as what is let's say the shortest distance between Walnut Creek and Redwood City, and that's actually a question that our GPS or navigation software answers every time you want to go somewhere. And we will actually study an algorithm that figures out the answer to this question in a little while. So this is another example of a graph. You might have heard this before, a knowledge graph. So a vertex in this graph can represent any object. So it's very general. And then basically any noun in our language can be represented as a vertex in this graph. And then what the edge in this graph represents, it's a relationship. Again, something very general on an action that's between two nouns. So the edge is kind of a verb. Okay, and so as an example, we can kind of see, let's say, there are two, Da Vinci, the artist, inventor, genius, is represented by a vertex, and then Mona Lisa, one of his painting, is represented by another vertex. And the relationship between these two is that Da Vinci has painted the painting Mona Lisa. Okay, so that's what this means. Another thing that another example is could be, this is the Eiffel Tower. Again, it's a noun, it's an object represented as a vertex, and then the city Paris, obviously another vertex in this graph, and then the relationship between the Eiffel Tower and Paris is that the Eiffel Tower is in Paris. So is in, that's kind of, a verb that describes the relationship between these two vertices. So that's what a knowledge graph is. A knowledge graph can actually lots and lots of interesting questions, such as an example here: who likes Mona Lisa? So in order to answer that question, then we observe that there is an edge called likes. So this kind of says, James likes Mona Lisa. So in order to answer the question who likes Mona Lisa, we just have to find all vertices that has an edge likes going into Mona Lisa, the vertex. Okay. Another question that can be answered, for example, is, what has Da Vinci painted? So in order to answer that question, we find the vertex that represent Da Vinci, and then we look up all the outgoing edges from Da Vinci that is labeled painted, and then all those vertices that the painted edge go into, those are the paintings painted by Da Vinci. And then finally, it can even answer questions that includes multiple vertices, such as, has James visited Paris? Well, we can look at James. The place that he has visited is the museum, Louvre. And then we can also see that the museum is located in Paris. And so by this small traversal here, we can see that James has in fact visited Paris, and that can be inferred in the graph. So knowledge graph can be stored in what's called a graph database. I'm not sure all of you might have heard that term before, but it's kind of similar to a relational database. And graph database even have its own query language, kind of like the SQL for relational database. So anyway, this is just two examples, and there are many examples of graphs that's described in your readings. And so as you can probably see, graph is an extremely useful data structure that we study in computer science. And so it's important that we'll study it well, and we'll spend the next week and a half or 2 weeks to study that. And we'll study a couple classic graph problems. First one is the shortest path between two vertices. And the next one will be the maximum flow between two vertices. And you will actually do an assignment with that. And then finally, we'll start what's called a minimum spanning tree in the graph. All right, so before we dig into details about graphs, let's kind of standardize on the graph terminologies. We already learned the word vertex or vertices, and they represent objects, and then edges that represent the relationship between objects. Now, one thing about the the edges is that they might have a direction or might not have a direction. So things that have a direction are things like in the knowledge graph, right? These have very specific direction and it has a meaning, right? Because Da Vinci painted Mona Lisa, but Mona Lisa did not paint Da Vinci, right? So there are graphs in which direction matters, and then there are graphs in which the direction do not matter, such as the distance graph. In this case, San Francisco is the same distance from San Mateo as San Mateo is from San Francisco, right? Um, so that's that. Now, vertex, as I emphasized over and over, can store any sort of information. Now, when we study this, it usually just stores like a string, a label that kind of identify the vertex. But again, note that that's not the only thing that can be stored in a vertex. By the same token, an edge can store any sort of information. Particularly in the case we see in the knowledge graph, it can store very complex kind of information. However, in our study, it usually just an edge usually is just associated with a number. We call it cost, weight, or something like that. So, and the number usually can represent distance between two vertices. In the case of distance graph, or when we start flow networks, then it can store the capacity for flows between two vertices, etc., etc. For those of you who are more mathematically inclined, from a definition of a graph is that graph consists of V and E. So V is just a set of vertices and E is a set of edges. And note that I use the word set here because usually the order of vertices and edges don't matter, although there are times that we will compare them. Anyway, and each of the edge is a tuple that is from a vertex in V and to a vertex in also in V. Right? And there are other commonly used terms such as path. Path is just a sequence of vertices connected by edges. So, and the only requirement is that the edges must be part of the graph, obviously, right? And then there can be cycles. And cycles, as we saw in the distance graph, is just a path that kind of starts at the same vertex as where it ends. Okay. Now, graphs that don't have cycles, they're called acyclic graphs, such as a tree. Right? And then finally, a directed acyclic graph, or commonly referred to as a DAG, is a directed graph that has no cycles. So again, tree is an example of a DAG. And speaking of trees, since we started with trees, let's conclude this video by comparing graphs with trees. And as you kind of already saw, graph it's a very general data structure, and tree is just a very specialized graph. So for example, tree, there is a singular dedicated node that is the root node. Whereas graph, all the vertices, none of them is a very specialized root. Right? And trees, and especially like for example in a binary search tree, each of the node has exactly 2 children, or less than 2 children. And these children, they are older, right? On the left side, the child is smaller, the right child is bigger. Whereas a vertex can have any number of edges, can have no edge, or 100 edges. And then usually these edges, they are not ordered, although there are times that we'll compare them. Right? And the edge between nodes in a tree, they always define a parent-child relationship, right? It contains no other information. But for a graph, the edge between vertices can represent any sort of relationship, right? And then finally, trees, there cannot be any cycles in the tree, right? Between any ancestor and a child node, there's only one path between them. But in the graph, we have already saw that there could be cycles, right? So that means that between two vertices, there might not be just a single path. There could be multiple paths. And these are some of just the main differences between graph and trees. And I'm sure you probably can come up with others.